the difference and similarities between statistics and data science. And so please ask questions. I will be moderating the questions, so ask the questions in the chat, and then I'll take over the conversation and the discussion at the end. Vinny is going to be speaking first, then Rob is going to follow, and we're going to have a last half an hour where we're going to speak to them, and I'm going to sort of handle your questions and create a really interesting discussion. Please participate. This event is for you. It would be great if you could have the camera on so that we could see you, so that we could see what's going on. And yeah, I guess that's it. Vinny, your turn.
Let's share my screen, 1 second. Can you see my slides in full screen? Yep, cool, perfect. Right, cool, thank you very much for the invite. So today I'm going to be talking about, my title is called Spot the Difference, Statistics, Data Science, Machine Learning, AI. So this talk was kind of originally inspired by kind of getting annoyed at people not quite knowing the difference and assuming things, the difference between these things that maybe didn't exist or exist in a different way to kind of what they think. So just tell you a little bit about myself before I start, kind of tell you why maybe I'm qualified to talk about this. So I did my undergrad and master's in Lancaster before coming up to Glasgow to do my PhD in statistics. I've done various postdocs, including kind of a postdoc in statistics in Glasgow, a research biostatistician role in kind of a health department in Leeds, and then I'm back in Glasgow as a postdoc in computer science, pretending I can use computers. And also do some consultancy in my free time, mainly kind of veterinary health and that kind of thing, but basically anything that it can be useful for. So why do I think I'm qualified to spot the difference, as the kind of the title of my talk kind of says. So I've worked in statistics and machine learning. I've worked in lots of different departments within those kind of areas, and I've kind of published and developed methods in all these areas. So I kind of feel like I've got a variety of kind of experience in these areas, and maybe I can kind of talk about at least what my experiences are, of what people consider the differences are, what maybe I consider the differences are. So that's kind of where I'm going to start out, and then I'm going to kind of look at maybe how statistics can kind of learn from these other disciplines and maybe kind of improve itself in that way. So I'm going to start off with basically what I'm kind of almost defining the subjects as, because that's actually quite open to interpretation. I'm going to kind of go with some of the stereotypes that people maybe associate with different areas. So people are not fans of statistics, whether that's potentially changed after 10 months of looking at various plots for COVID is questionable. I'd kind of be interested to see. People are not fans. There's several reasons for this. In research, everybody needs statistics pretty much. I think that's a universal statement, but most people did not do a statistics degree and therefore don't want to do statistics, in the same sense that I avoided writing by doing a master's degree. Similarly, the media gives you some absolutely terrible coverage of statistics. I don't think this is actually a genuine media image, but they do come up with some absolutely ridiculous statistics, and the politicians do their best to abuse statistics in any way they can. Statistics get blamed for terrible data summaries. For instance, this one, this poor woman getting married quite a lot of times. And finally, statistics has a reputation maybe in kind of research and industry, especially, of being very basic. People think of maybe statistics research as being whether your p-value is more or less than 0.05, which is obviously very harsh, but it's kind of something people do actually think. Machine learning, people kind of think almost the opposite. People think of machine learning as being this very, very clever thing. Apparently this is I don't know whether this is a genuine Bill Gates quote, but I think it is. There's basically a lot of machine learning used in industry, and people are very excited about its prospects. So people think that machine learning can solve all their problems. Whether that's the case is another question. People like to go and apply algorithms to data, and they, as kind of this cartoon suggests, they don't always get out what they hope. People think machine learning is much more advanced than statistics. People think that machine learning is clever, even if you do something very simple. There's a reputation, I guess, from a statistician's point of view that machine learners probably don't bother checking their assumptions. In this particular diagram, they just, fudge the model until it works, which is kind of, I guess, the reputation machine learning has from kind of your statistician's point of view, or at least a number of statisticians I know's point of view. And in a lot of funding, calling something machine learning gets you funds. So in my experience in Leeds, there was a lot of calling statistics machine learning in order to get funding and pretend something was cleverer than it actually was. Data science is an interesting one. It's obviously quite a new field, but it's on the huge expansion right now.
Vinny, sorry, if you don't mind me interrupting, 1 second. It seems that people are having some issues with the sound, and so I don't know if there's something that you can do, or maybe you could speak a little bit slower so that the jitteriness is not so noticeable.
Okay, I'll go a little bit slow. I think that's probably the best I can do. So my laptop's not maybe the best for this. But I'll try going a bit slow. Thank you. Let me know if it's not improving. So data science encompasses aspects of statistics, machine learning, AI. So there's kind of lots of mathematics behind it. There's lots of data, and there's kind of a combination of subject expertise, whether that be kind of industry or research-based. Data science covers quite a range of areas, as I'm kind of interested to see what Rob kind of says on this. There is kind of there are data scientists that do Excel, and there are data scientists that do deep learning. Is this sounding better, by the way? Marginally? Okay.
But it's better when you talk slower.
Okay.
Thank you.
So data science employs people with a large variety of skill levels and job descriptions. I guess that kind of relates back to my previous point. There's very high level data science positions, and there's very, very entry data science positions that all kind of get called exactly the same title. Data science potentially has a reputation of being flexible, potentially not done very well. I guess that kind of relates back to my previous point. You can have people from a very wide variety of backgrounds that potentially means you end up with a wide variety of kind of skill levels. Artificial intelligence is really the harder of the four things to define. In essence, it's kind of potentially mainly a buzzword. But then you could argue that it's also behind some of the biggest technologies around. Your kind of your driverless cars, your facial recognition, your natural language processing, your kind of very high level, clever, big industrial kind of things Vinny, that we're interested in right now.
I'm sorry, I'm gonna have to stop you there again. It just seems like the problem is still going on.
I'm gonna have to try a different computer then.
No, we're all trying to turn our cameras off, see if that makes it better. I'm sorry everyone for the interruption. I guess we're all used to technical difficulties by now. It is the end of a very exhausting year.
Your camera off.
Okay, I'll try turning my camera off. Should I try again, or?
That sounds a little bit better. Maybe if you could go back a couple of slides, okay. Back to where you were talking about the some data scientists that use Excel and the other ones that use deep learning. Yeah. Okay.
Try again.
Go ahead.
Sorry, I've had issues.
Oh God, no.
It sounds kind of like interference or something, Vinny. So I don't know if it's your headphones.
It's better with the headphones generally, but I can try without. Is this any better?
That is much better, yes.
Oh, okay, that's weird. Let me just turn my sound up then. Apologies, normally it works a lot better without the sound. With headphones. Still okay?
Somewhat better.
Yeah. I'll try going slowly again and see whether that works. Yeah, okay. So I'll go back to the bit on data science. The data science kind of encompasses a wide variety of subjects, or statistics, machine learning, data, or subject expertise.
Vinny, sorry, this is just so painful, but it does not seem to help. I have an idea. Sorry?
A couple of minutes and I'll change computer.
Sure. Yes, I have an idea. Rob, why don't you take over? I know that you were looking forward to being second in this presentation, but maybe you could take over the show, and then that'll give Vinny some time to change computers, and then maybe we can start over again. Sorry, everyone, for the complication.
Okay, no worries. Yeah, don't worry about it, fella. We will think on our feet. Right, I'm going to try and share my screen. Hold on. There's the button. Your screen. Can you see a blue screen with an MBN badge in the corner?
Yes, we can.
Hey, great. Right. Okay. So who am I? I've spent the last 20 years now recruiting primarily for roles within analytics and data. In the days before they called it sexy data science. I'm the guy that designed, built and scaled up the Data Labs Masters Placement Program. So I've had some very specific experience working with graduate statisticians over the course of the last 4 or 5 years. The business I work for are the delivery partners for Data Labs Placement Program. And a few years ago, it was me that actually built the model. I work as an advisor to the University of Glasgow School of Maths and Stats, an advisor to the Data and Marketing Association on talent, an advisor to Scottish Government on the AI strategy document. I worked within the Skills and Knowledge Working Group. Was awarded the Data IQ 100 title in 2019 and 2020. I am rated as one of the 100 most influential data practitioners in the UK. So that's nice. So hopefully I can teach you something today. The slides that follow, it'll last about half an hour, and it's a load of stuff that I've kind of pulled together based on an external view of the marketplace. I am looking for interaction, so if you have any questions at any point, please just drop them into chat and Sebastian will moderate them at the end. I don't expect you all to agree with everything I say. As I say, this is a window on the market. It's the market's view rather than my own personal view. So let's just crack on and we'll see how we go. I suppose the first thing to do is to check audio. Is my audio coming through clear, or is it skipping in the way that Vinny's was?
We can hear you perfectly, Rob. Thank you very much.
Okay, fantastic. Okay, some of the stuff we're going to look at, some of the main data job types that are out there at the moment, the skills required for each job type, the different hierarchies, what the food chain looks like, how much you will get paid, which is always a quite important part. In the confusing world of data recruitment and how to be less confused by it, I acknowledge it is a confusing world. And for anyone that spent any time looking into the window of potential employment, it can be very confusing. Vinny's slides were starting to tell this story of where statistics, data science, machine learning, artificial intelligence overlap. Looking at it from precise definitions, know now and forever be aware, those precise definitions do not exist in industry. Everything in data tends to get lumped into one big giant bundle, and it's up to you, the reader, to work out what exactly is what and what you're most suitable for. So I'm going to try and help you with that. So if you were to enter into commercial data, your job is in here somewhere. Now, I'm going to issue a caveat here before we go any further. I am not a graphic designer, and I work for a small-ish organization that doesn't have an expert in creating marketing infographics. So when you're not a graphic designer and you don't have an expert to draw infographics for you, What do? You steal things. So the infographics contained in my slides have been shamelessly blagged from other sources on the internet. So some of the stuff might not be 100% accurate, but without the ability to alter them, because I can't, this is what I've got. So if you just look at these 6 circles, we've got different fields that, if you break down that word data into what commercial people actually do, it sits roughly around these 5 external circles. So if we go from the top, the data management people tend to be technologists that manage the asset. If we go to the right, the engineers or the developers that build the thing. If you go down bottom right, the business analysts work as conduits between the data people and the commercial people. Down in the bottom right corner, we've started to get the specialisms around machine learning. And in the top left corner, we've got that kind of classic data scientist. And we'll break that down in a little bit of detail. Now, the terminology big data, I think now is a little bit superfluous, because the vast majority of data roles that I'll deal with all work with big data, and that's data that's complies to the classic 4 or 5V model. I'm sure you're all very familiar with it. So when I recruit, I tend to, or my organization recruit, we tend to find people that fit into one of these 5 categories. Use my own words here, so please excuse the vernacular, but the data scientists are all about building stuff, maths and problems, and talking about the results. The data engineers and developers are about building things, making those things big, and then most importantly, putting them into a production environment. In other words, making them not just a one-off R&D project, but a scalable, reproducible, robust production. Then you've got the data management people, as I mentioned. They're all about curating, understanding the legalities of things, and liaising within the organization to teach other people what they can and can't do with that also important data. And then down in the bottom right, we've got the analysts, the people who extract data, investigate what has been extracted, form a conclusion, and then talk through that conclusion with the rest of the business. And right in the middle, we've got this increasingly important within larger corporate organizations, this almost thoroughbred reporting individual. There's some part data scientist, there's some part data analyst, but effectively they're becoming known as, more and more now, you hear the vernacular used, the data storytellers, extracting data, visualizing it in an aesthetically pleasing way, producing reports, dashboards, and different forms of graphic medium, and then talking through what those reports look like. And particularly in Scotland, particularly within some of the very large legacy organizations we have, like the banks, we see a lot of people whose actual specialism, they may have studied statistics at university, but what they actually do for a job is produce these very complex visualizations and obviously be able to talk around what these visualizations actually mean. So they're the main role types that we work with. Now let's have a look at them in a little bit more detail. The classic data scientist, and right away, I would point you to the top left corner. It is almost accepted as standard that this individual will have a background in mathematics and statistics. That individual will also, as a data scientist, have some knowledge of how to program. That means the ability to code. We've then got the bottom 2 sections, which are the domain knowledge and the communication and visualization. Now that visualization relates back to the reports building, the building of graphical pictures, if you like, that tell a story, but then the ability to talk around that story. But then in that bottom left corner, there has been so much of an emphasis placed on this over the last few years that it wouldn't be fair for me not to pause for thought here for a second. I have a slide dedicated to this later on, but the simple fact is that commercial organizations need individuals with the ability to not only communicate effectively in verbal, non-verbal, emotive terms, but also to very quickly absorb knowledge and understanding of the actual domain they operate in. So to give you a classic example, we do a lot of work for very large engineering companies. Their data scientists must know the terminology, the jargon of engineering. They must know the language used by individuals within that engineering environment. So these four things are now included as being almost the essential toolkit for data science. Moving into the engineer, as I mentioned earlier, these are more of the builders. Now, a caveat here on this slide, some of the languages in the top right corner have now been replaced. It is now much more common for data engineers to work with cloud-based data storage that is rented from organizations like Amazon or Google or Microsoft. So the language there is a little bit outdated. This individual would build, construct, whatever you want to call it, robust, productionized data architectures. In other words, the data scientist can't do their job without the engineer building an ecosystem that allows huge amounts of data from a huge number of sources to exist flawlessly within the organization. So the mindset there is somebody who can effectively move between architecture, development, testing, productionizing, and all the while has a huge bank of knowledge regarding the repository of data, whether it's stored in the cloud or on premise, whether or not it's a database, a data warehouse, a data lake, or whatever the next iteration is called. This individual is the person who is the subject matter expert for that storage. Then looking at the manager, now I touched on this slightly earlier. This individual we are seeing becoming increasingly important, particularly when we look at things like GDPR or some of the legislation which sits around the use of data within organizations. It is common for this individual to have a solid understanding of the law, a solid understanding of organizational commitment, solid understanding of efficacy. This individual is almost the custodian of the data. So on one hand, we'll have a very solid technical understanding, but on the other hand, we'll have a very strong commercial slant. This is effectively the person that will tell the engineer and the scientist, yes, you are allowed to do that, or no, you're going to break a rule, break a law, or break a code. In the analyst, the analyst has the ability to extract data, to analyze that data using a whole range of sophisticated tools and methodologies, then very importantly, to provide insight of what that analysis actually means to the business, and to be able to talk the language of business with individuals who firstly care very little about how that data was extracted and analyzed, but secondly will have a very strong agenda for what they want the analysis to produce or to advise on. So this individual is part technologist and part negotiator and diplomat, and a hugely important part of the kind of data ecosystem within organizations. So I've mentioned it, and I've got a slide all about it. It doesn't matter where your career takes you, what trajectory you plan to move in. If you come into a commercial organization, you are absolutely required to be able to communicate with other individuals. Now, in the first instance, those other individuals will work within your own team or your own business area, so other data scientists, other data engineers, other data analysts. But then that communication will then need to happen outside of the world of data. So whenever I've worked with data scientists, I mean, I would normally be found within the human resources or operations organization. I don't sit in a data team. I'm not a data scientist. So any data scientist that I work with has to be able to translate their how can I put this, very complex theoretical understanding of complex subjects, and they've got to break that down into layman's terms. And all data roles need to be able to do that. It doesn't matter how good a data scientist you are, you can't interface effectively with non-data. I'm not just talking here about verbal communication. I'm talking about non-verbal cues or the ability to write very concise, accurate reports. Absolutely essential skill for any data professional. And the reason I put so much emphasis on this, my work with particularly student groups over the last few years has shown to me that there are certain personality types that are attracted to work within statistical, analytical, and mathematical fields. And often those personality types are not the most outgoing, gregarious, communicative types. I recognise that. I mean, I've got a son sitting next door that's studying the same stuff as you guys. But the point is that you've got to work on this communication, because as the bottom bullet point illustrates, it doesn't matter how good you are at being a statistician or a mathematician or whatever it is you want to be. If you can't communicate with people like me, you're going to find yourself very, very frustrated in your career. So, top tip, practice your verbal, non-verbal, and written communication as much as you possibly can, and wherever possible, practice it with commercial people. And I know earlier Kate was asking for people who wanted to get involved with the society. If that's an opportunity to practice your communication skills, take it. If it's mentoring, take it. If it's working in a support capacity with a charity, anything that's going to get you an opportunity to practice your communication skills, it will be worthwhile when you enter into industry. You will make a massive difference to your own career trajectory if you are able to communicate with non-data professionals. And what that means is, as I mentioned, breaking down the complex into simple, understandable, bite-sized chunks. I don't care about the working, I just care about the result. So, having a look at some of the career progression routes, we can see these are normally increments of, say, 2 to 3 years, perhaps a little bit more. And at the point of senior data scientist, what an individual is normally asked to do is to separate out into one of two areas. One on the left-hand side would be, shall we call it, a tools specialist, a domain expert, a highly experienced individual who just does data science work. But on the right-hand side, when you have somebody who's got additional responsibilities for the work and output of other individuals. It could be mentoring, it could be management, it could be some form of leadership. But obviously the balance there is that somebody who follows the management route probably isn't going to stay as current on the tools and technologies as somebody who chooses to specialize in their career on simply being a doing data scientist. But that's what it kind of looks like. And the little increments between each step are normally 2 to 3 years for most individuals. The engineering, and the only slide I could find that made sense here had Hadoop. So just replace the word Hadoop with data developer, data engineer. You see exactly the same type of progression, 2 to 3 year increments. And you see again that split between somebody who takes responsibility for the outputs of others and somebody who chooses to focus on actually the tools, techniques, and technologies themselves. Now, there is sometimes an additional career path on both the data scientist and the data engineer, which I would call consultant. And they are individuals who perhaps work for consultancy organizations where their role is to be a practitioner, a doer, a tools person, if you like, but they have a very commercial edge to what they do because they're working on behalf of a client organization. Therefore, very strong commercial skills are also required. So if you add that into both the scientist and the engineer career path, you can see sort of 3 routes: tool specialist, commercial consultant, and manager/leader. The data management, again, same type of idea. This particular example has been taken from a pharmaceutical type organization. You've got the person coming in at the bottom maybe designing or in some way structuring database. As they move up, they start to assume responsibility for the management of the actual asset itself. So data management doesn't necessarily mean the management of individuals who do data things. It means more the management of the estate and all of the accompanying legal, commercial, and ethical considerations that go into managing that estate, and then moving on up through lead and then head. Now, where we see this in Scotland a lot is within organisations, particularly in the healthcare sector, or again in financial services industry, where we are dealing with sensitive data. That's where you'll find people whose sole role is the stewardship of that data. And then finally, perhaps the most complex is the data analyst. Now, when we recruit for data analytics, that could be everything from insight analytics to CRM analytics, to econometrics, to pricing analytics. So there are some different career paths and routes here. So the data analyst probably has the most choice within their career in terms of where they want to go after the first couple of years are done. But you can see the management route, the tool specialist route. There's even a crossover we see a lot with data analysts moving into data science, perhaps upskilling, getting the programming skills and moving in a slight sideways direction. You also see some of those more specific domains at the top there, finance analysts. And as you can see, it's quite common for people who specialize in financial analytics to eventually move on to roles like finance director or CFO within larger complex organizations. But you also see some of those other career paths there. And again, think 2 to 3 year increments, probably looking at a person spending anything between 5 to 10 years to maybe move to that right-hand side. So what does it mean in real terms? Now, I benchmarked this using a tool called IT Jobs Watch, which I would strongly advise if you're interested in benchmarking where you might go in your own career. You have a look at IT Jobs Watch. What it does is it scrapes advertised salaries from basically internet adverts over all time, and it does it in real time. So you can have a look at trends, and you can have a look at whether roles pay more now or whether they paid more last year or they pay more, in different parts of the country. But I used Edinburgh as a start point here because that's just where we've got the biggest proliferation of data people in Scotland. Almost everybody coming out of university with an MSc in their hand will be somewhere between 25 and maybe 35k as a starting salary. With a PhD, obviously that would be a little bit higher, but most of the time I'm dealing with MSc qualified individuals. Then once you've had that 2 to 3 years worth of experience and you start to develop expertise, you can see the jumps. Some of the roles do jump a little bit more than others. At the moment, there's a particular demand for data engineering skills in organizations. That's largely to do with the, the kind of the gold rush for data science, say 10 years ago, has now led to loads and loads of great work now needing to be put into production. So we've got loads of companies looking for great engineers, thus the money goes up a little bit. Once you hit that top level of kind of a department boss, if you like, you would be looking round about 100k on your basic salary. And remember, that's for Edinburgh. If you were to travel outside of Scotland, that could probably be quite a bit more. I'm actually working at the moment on behalf of a very well-known media brand. Their chief data scientist will probably get about 150k. Their chief data manager, same kind of idea, 130, 150k. So the further south you go, the more the money rises. But roughly speaking, in Scotland, you'd be looking at around about 100k once you'd spent probably 7 to 10 years in role, roughly. The key question, do companies know what they want? These wise old owls out there in the commercial world pontificating and sending out their pronouncements and judgments, do they know what they're talking about? Nah, they don't. Well, the caveat there is that some do, but a lot don't. And it's a massively confusing world out there where, as I mentioned at the beginning, commercial organizations don't follow the rigor of academia when it comes to naming things. They'll just call it whatever they like. And we'll go on to talk about why that happens. Just be aware in your mind as we move through. Companies don't always know what they're talking about. It's as simple as that. You'll sometimes come to guys like me and say, are we saying the right things? And I'm like, no, you're not. So let's think about it and break it down a little bit. How does it all start off? It It starts off with a technical person, and let's call them, for argument's sake, a data scientist, or we'll call them a statistician or an analyst. And they decide they need to hire. And they write down on a scrap of paper the 3 to 5 things they really want somebody to be able to do. But that thing that they want somebody to be able to do can sometimes be a little bit of a wish list. It might be stuff that they need, or it might be stuff that they want, and it might be stuff that they think might be useful at some point, but they aren't entirely sure why. They're just kind of writing down a wish list, if you like. But that started off within the technical team. And most individuals know if you're working within a larger complex organization, it's not always the technical folk who do the hiring. They then pass their wish list over to an HR person or a talent person or resourcing or recruitment or people or whatever they call that function. That team's got a different agenda to the technical folk. This is where things like company culture come into play. This is where things like diversity and inclusion come into play. This is where things like succession planning come into play. So the HR talent agenda is different to the technical agenda. So suddenly our little list of 3 to 5 things that we need it just now and we might need some of this, that gets augmented with another 3 to 5 things that could be aspirational and could be contradictory. Then it goes up to the top of the food chain, the C-suite, because if we're going to hire, we're going to need sign off from the CFO, and the CFO speaks to the CDO and the CCO and the CEO, and all that C-suite, they throw in their own ideas and their own slants and their own buzzwords. And they've seen what their competitors are doing, and they want a slice of that. And they think that this is going to be cool, so they add in a bit of that. And before we know it, we've got a very messy and confusing situation. That messy and confusing situation is often an advert or a job description. Get it through, and it is just a lot of people saying a lot of different stuff. Some of it. How do we avoid this confusion? By taking some simple steps. Firstly, understand from those very rough categories that I provided earlier on, understand which of those main job types your education and background is most suitable for. If most of us on the call are statisticians, then right away I would say data science, definitely. Data analytics, definitely. Data management, possibly. Data engineering, possibly. So right away, have an understanding the likely direction of travel. And then secondly, start to tailor both your offline and online presence around that main job type. So you're starting to almost think your own future. Make sure that everything you do is tailored towards that. So you've made a decision you want to be a data scientist. Everything about you, the casual reader, should suggest data scientist. And then when you're looking at adverts and job descriptions, look beyond the job title. Remember, the person writing that job title may not truly understand what that job is. Most likely in a large complex organization, the person writing that job title is a human resources person. And although the technical team asked for a statistician, by the time it reaches the market, it might say data consultant, because that's what the human resources C-suite decided it would be cool and trendy to call it. So the first tip I'll give you is to look beyond job titles and look carefully at the responsibilities. Then we come back to that idea of that little scrap of paper being passed between these different teams. The first few things written down are usually the needs. When I consult with organizations, when I reach them, it tends to be at the point in time that they've written down all these things on a bit of paper. And what I ask them to do is to take 2 other bits of paper, on one, write in red, the needs, and on the other, write in green, the wants. Because organizations hire on what they need, not necessarily on what they want. That's nice to have, and those wants can often be trained or coached into individuals who have got what the company needs. So you, to avoid confusion, focus on the first few requirements that are primarily usually the needs. So what that means is when you see the big list of 10 things and you go, oh my God, I've only got 2 or 3 of those things. Well, if those 2 or 3 things are the first 2 or 3, I would consider applying for that role. Make sure if you are applying for a role that the needs are fully, clearly reflected, very visibly on page 1 of your CV. What that I've done with student cohorts in the past, the single biggest reason for not making it to interview stage is not clearly showing somewhere in the middle of page 1 that you've got the needs. When my organization put an advert out for example, a data scientist for a London-based company, we can receive dozens of applications. We're working against the clock, we're under pressure, we've got clients shouting at us. We've got to get our shortlist back very, very quickly. If your CV does not clearly demonstrate the needs very quickly and readily on page 1, the chances are the person reviewing your CV will overlook it because they've got other CVs that scream suitable in their face. So they won't necessarily spend a lot of time going through every bullet point in your CV. So make sure any needs that you see on the job spec are clearly listed on page 1 of your CV. So how to do it the other way around, searching for jobs using your skills. So another technique that I would use is to look for roles that use the technical skills that you possess. So in this example, I've given Python. You could easily replace the word Python with statistics. Search purely on that skill, ignoring the job title. Again, giving you that idea that what they've called it might not necessarily be. Use something like Indeed or LinkedIn. You should be able to do a very simple skills-based search, which will give you different visibility of opportunities that may not have come up if you just searched on the job title. So what I mean by this is, say you want to be a data scientist, you're obviously going to search on data scientist. I would also suggest that you search on data science, then search on mathematics or statistics, or if you've used MATLAB or SAS or SPSS or whatever it is, search on those actual skills, which will then give you a whole different range of roles. Learn to mix it up and use these different approaches for different types of searches. If you get to interview stage, carry out these simple tasks in order to determine whether or not it is the right role for you. Now, I've got a simple methodology when it comes to interviewing. Interviewing should always be a two-way flow of communication, never an interrogation, always an exchange of information. So make sure if you're going for an interview, you'll be able to determine if it's right for you. Number 1, research. The start point for anything that's to follow. Ensure you research organizations. Think about looking at these 3 things. What do they do? Who do they do it for? What other organizations exist in their universe? That could be competitors, it could be suppliers, it could be affiliates, but get a good understanding of what they do, who they do it for, and what other organizations exist in the universe. In the commercial world, most companies do something for somebody else. B2B, other businesses, B2C, consumers. So do that research and research the role. So understand from that wish list what they want somebody to do and what they need somebody to do. Then start to prepare examples of where you've used or studied what they need. Now that could be a commercial example, it could be an example from voluntary work, it could be an educational example, it could be an academic example, but think in your mind. They've said someone needs MATLAB. I'm going to think about where I've used MATLAB in the past. Then, very importantly, prepare your own questions. Remember, it's an exchange of information. Your own questions can determine whether any role is right for you. Remember, you know what you like, you know what you've studied, you know what you want to do, you know what is going to make you happy. So by preparing some questions around the needs, we can understand what those needs are actually for. Specific example here, I saw Python on the job description. It was near the top. I can assume it's a need. So I'm going to prepare 5 questions all about Python. What do you guys use Python for? What version of Python are you using? Why are you not using R? What training will I get in Python? So you're thinking about questions on the needs. Those needs will always usually be tool and technology and technique based. Learn to follow up your questions with a series of additional questions which will very quickly allow you to understand how much of your time roughly will be spent on each need. And the perfect way of asking this type of question is, you've said Python's a need. I understand it's crucial to this role. How much of my day will be spent programming in Python? Extrapolate that over a week or a month, get an understanding of how much of your time will be spent using this skill. We'll be able to determine whether or not that job is the right thing that you want to do. Tip. There are other roles out there that could be suitable that aren't classic data roles. So the type of organization that has a large data asset will have a hugely complex ecosystem of differently skilled individuals, but some of them will have very similar core skills. By that I mean a good data background is looked upon very favorably in areas such as business analysis, any area within digital marketing or e-commerce, which has had a huge boom in the last year, and the actuarial sciences. More and more product roles are now being focused on people with mathematical background, anything to do with the analysis of complex systems, and even things like software development, particularly when it starts to overlap with areas like DevOps. We're seeing more and more individuals with mathematical statistical backgrounds moving into roles that are classically out with the data domain. I'm working on behalf of a client at the moment. They're a software company. They make software that's used for simulation modeling, and they want their software developers to be mathematicians or statisticians. So there are loads of roles out there that people with your background could be suitable for. It's again back to that little formula of looking at the job description, focusing on the needs, seeing whether or not those needs are things that you have skill in or are interested in, and just following that simple process again. You have the advantage in many of these roles because more and more organizations are looking at the complexity of the product or service and deciding that, well, although this role may be in an area like digital marketing, it would really help if we had somebody with a very analytical mindset in there. So it's opening up a huge range of other opportunities. Again, you follow the same process. Look to separate out the needs from the wants. It's not that difficult. As I say, the needs are usually near the top. And then focus on whether or not you've got the needs. So, quote to live by a lady I've worked with for a few years now. Focus on being really, really good at the thing you love, rather than being average at lots of stuff. Focus on what you love and be excellent at it. Hopefully, good things will follow. Thank you very much for listening. If you have any questions, feel free to shout away and I'll answer them when Vinny's done his thing. Thank you.
Thank you, Rob, very much for your great slides and your great presentation. It's there's really a lot of food for thought, let's say.
You're very welcome. Thank you.
Vinny, if you would like to go again.
Can you hear me better now, hopefully?
We can hear you really well. And if you just want to sort of share your slides and then we can...
Sorry, I'm on an unfamiliar computer now. Can you see some slides?
We can see some slides and we can hear you well.
Excellent. Right. Apologies about all that before. Usually my computer is okay with headphones when there's lots of people, but not today. So obviously borrowing someone's computer, as you can tell by the slightly different name, which apparently I can't change. So I'm just going to kick off where I started. Hopefully I've not missed, hopefully you heard enough about the first few sections that's enough. I don't think it's the most important section of the presentation, so hopefully it should be okay either way. So I'll start back on kind of my definition, I guess, of data science. I've kind of gone, I guess, more general than Rob's kind of descriptions, but I guess my data scientist is more towards, you know, the data analyst, data scientist, as Rob called them. So, you know, data science can encompass lots of aspects of kind of statistics, machine learning, data, you know, product knowledge, as kind of Rob was talking about for the individual companies. As a kind of, again, as Rob was saying, it can involve lots of different kind of skill levels and areas. It can involve people doing, you know, Excel kind of work and databasing, all the way to kind of deep learning at kind of your big tech companies. And that means that kind of data science employs a variety of people, again, as kind of Rob's been saying, and it kind of means that, again, as Rob was saying, it's kind of difficult to determine between the different roles as to which ones are suitable for you and which ones maybe aren't. The one thing for me is that data science can have kind of a reputation of being very flexible, in the sense that to be a data scientist, you tend to have a lot of different skills, whether that could be kind of programming and statistics and machine learning and all these other things. And it can kind of mean that it's not necessarily done well, kind of, you know, everyone trying to be the jack of all trades, I think the phrase is. So AI is kind of the newer buzzword of all these things. AI is getting the credit for a lot of the very cool inventions that we're starting to see that use, you know, deep learning and neural networks. You know, kind of your space shuttle, your chatbots, your facial recognition, your cars. But often, you know, people use AI as a buzzword. Companies are doing something very simple and pulling AI in an effort to kind of oversell what they're doing and give the impression that their product is superior to what it actually might be. It is, but as I said, AI is behind some of the new technology, so it should get some kind of credit where it's due. But you also have a big problem with, this is maybe an industry problem, but this particular example is from academia. I've heard clinicians basically wanting to use AI on their data because they think that's going to solve all their problems. And they basically want to jump from doing a t-test to using AI, which is not really a viable thing. The other problem with AI is there's a lot of people, because of kind of the open technology drive that kind of is in a lot of research these days, with kind of everything being available online to use for free, people can just use AI. And that means that people are using these black box things that they don't really understand and just kind of getting into the problems that can come from that. So the next section for me is to look at kind of what is the difference and similarities between, say, statistics, machine learning, data science, and AI. So I kind of tried to give a few examples of where they're very similar, where they're quite different, and where it's more kind of maybe an application difference rather than a technical difference. So I found this, I was sent this very interesting diagram. It was called the Pillars of Machine Learning. And I find it kind of interesting as someone from a stats background. I looked at it and went, regression, that's statistics. Dimensionality reduction, yeah, that's statistics. Density estimation, that's statistics. Classification, yeah, well, that's statistics. But you can kind of say that with all these things. And I kind of thought, well, could you just replace machine learning in this diagram with all of the above? I think you can. I think you could stick statistics at the top of this temple, I guess it is. And I think you could stick AI, and I think you could stick data science. So it kind of suggests that there's kind of a lot of overlap in the kind of core principles and the kind of mathematical based skills and kind of implementations that are behind a lot of these methods. So as I said, there's a lot of shared methods, but that kind of comes from the fact that in each of these methods, we're interested in the same thing. Whether we're interested in kind of prediction, so kind of you might be interested in predicting, you know, future financial markets. We're interested in classification, whether that kind of be disease, customer types, you know, Netflix movies. And we're interested in extrapolation, so kind of predicting the future or predicting some unknown. And this is the same kind of all of these topics, and hence why there's kind of a lot of overlap between the methods. So I kind of had a look at this then in terms of teaching. So I'm kind of interested, obviously I'm still at the university, so I'm kind of interested in kind of teaching and kind of how the different subjects are taught. I looked on Coursera, the online learning platform, which I'd recommend if anyone's ever interested in learning new things. And Andrew Ng's machine learning course, which is one of the most popular courses on Coursera, spends the first 3 or 4 weeks looking at regression and statistics. Similarly, so does the deep learning course and the data science course, basically a mix of statistics and machine learning. So basically all of these have exactly the same foundations. So basically all your kind of entry level machine learning courses, your entry level statistics course, in essence cover the same subject with almost kind of a different way of looking at it. So it kind of leads you then into a situation where there's kind of a lot of ambiguity between methods. A lot of applied researchers have kind of worked out that if they call their statistics machine learning or AI, that, you know, they can get a lot more grants, funding, and papers. Similarly, kind of you see it in industry, people call very, very simple things, and they just very, very simple statistics, and they just call it machine learning because, well, that makes everything they look sound much more technical. They can get, you know, government grants, they can sell their product a lot better as kind of the forefront of technology. So, you know, there's a few examples of this that I've kind of found over the years. So this is an example, AI used in a really cool Nature paper. So the title is Robot Chemist Uses AI to Discover New Molecules. It turns out they used linear discriminant analysis, which is very much, I would call, a statistics method. And, you know, it was developed by R.A. Fisher, which again suggests it probably is a statistics method. But I don't think it would quite sound the same if you said basic statistics discovers new molecules. It's not quite as interesting as robot chemist uses AI. Similarly, you have this example from industry, someone using the AI equation that is called linear regression, apparently, which is apparently used to do website search engine optimization. I very much would not trust this company to do website search engine optimization, but again, it's kind of an example of a company overselling statistics in order to kind of call it something else and seem more technical than they actually are. So kind of, this is what kind of we get to then, is that the kind of machine learning, AI, data science are all kind of using statistical principles, but somewhat rebranded. You know, if you call it something slightly different, you end up with the same result, but people are more impressed. So it's kind of led me to think about things, about what things are similar, methods are similar across the different disciplines, and which ones are different. So the classic example that my PhD supervisor used as an example for me was Gaussian processes and kriging. So Gaussian processes are very popular right now. They're kind of the forefront of a lot of technology, you know, deep Gaussian processes, that kind of thing. And kriging is a very, very old thing that no one really considers anymore. But they are actually the same thing. It's just the Gaussian processes are a machine learning way of calling them, and kriging is the old school spatial statistics way of calling them. Another example is kind of hypothesis testing versus A/B testing. This is another kind of example where people use A/B testing as a way of describing statistical hypothesis testing, but making it sound really clever. In practicality, there is some differences in the sense that A/B testing maybe has quite a lot more coding built around it, so it's kind of, I guess, more technical in that sense. But in essence, it is just doing the same statistical hypothesis test. Is A better than B? Is H1 better than H0? I also found this kind of interesting glossary of terms between statistics and machine learning. I think the classic one being weights and parameters, or weights and coefficients. So taking exactly the same model, people from different backgrounds will say different things. And that's kind of, again, just a difference that just people just don't quite see, but it's kind of something that differentiates the two, but almost in a way that's just more practical rather than actual theoretical. I did find, not sure how much I trust this glossary is, I did find this, and I have never been invited to a meeting in Las Vegas to talk about statistics, but if someone wants to, they're very much welcome to invite me. Can everyone still hear me okay? Yeah, we still?
We can hear you well.
Yeah, cool. Just so I can see messages in the chat, I was just making sure it wasn't about my microphone again. So again, but there are some differences in techniques maybe between computer science, machine learning, sorry, and statistics. So let's take kind of linear regression. So most people here, statisticians, will have learned ordinary least squares, your kind of top equation, and they'll have kind of worked out the maths behind it. In computer science, you'll have probably seen, or machine learning kind of backgrounds, maybe data science backgrounds, you probably have seen the bottom version. In essence, they're exactly the same. The top one is just the solution to the bottom one. But, you know, so this is again an example of statisticians learning one thing and machine learners learning another thing and getting the same thing. In practicalities, we probably use the bottom one because that's kind of what is going to be inbuilt into things like R and Python, because that's the more efficient one because it doesn't do the nasty matrix multiplications. Again, parameter estimation, that can be almost the same but different across the different disciplines. So statisticians like to maximize likelihoods. That makes logical sense to statisticians. Machine learners like to minimize cost functions. It turns out that's exactly the same thing because you can just use a negative log likelihood as your cost function, and you know we have exactly the same thing. We're maximizing something or we're minimizing the negative of something. It ends up being the same thing. Some people just find one more natural to think about the other than the other. I have to admit, I've kind of got into the cost function way of thinking things recently. There is also different ways of doing inference, which you'll kind of see probably more in the research background. So kind of, if you do your kind of PhD or your research in machine learning or statistics, you'll maybe see this difference. Statisticians love MCMC, the EM algorithm, because it kind of gives you, well, especially MCMC, because it gives you supposedly an exact solution. Machine learners don't like it because it takes too long. And they like to use approximate solutions, which scare all statisticians because they have, you know, they don't have guarantees that the statisticians like to have when they do things. There is arguments that maybe the statistical guarantees aren't as kind of useful as we might initially think or have been taught during our undergrad as statisticians. There's different attitudes as well, which I think is an important one to kind of come to. So MCMC convergence checks, again, using kind of a simple example. Statisticians love them. They love our hats and their Gelman Rubins, and the name I have no idea how to pronounce. Machine learners would not in general ever do convergence checks, just beyond visually looking. And I was told at a machine learning conference, you check parameter convergence. Wow, you must be the only people still doing that. And this wasn't like a full machine learning professor. This was a guy that still did a bit of statistics. There is this kind of flexible, strict attitude between statistics and machine learning, which is maybe starting to change as kind of statisticians move more towards data science and machine learning. But it's certainly a thing. Statisticians like rigor. They like things to be kind of proved and work in theory. So, you know, law of large numbers, that kind of thing. But a lot of these things do require some constraints, such as large N or infinite N, to actually be guaranteed. And machine learners will argue that that's actually, well, if you're never going to get large N, well, that proves pretty irrelevant. And therefore, we may as well just use whatever we think works. In terms of maybe practical things, maybe this is more for applied people or for industry, the goals are often different between statistics, machine learning, data science, and AI. People tend to think of statistics as being all about kind of explaining things and kind of what does age affect your chances of surviving coronavirus, for instance? Whereas machine learning tends to be all about, is someone going to survive? It's all about the kind of final prediction. Is someone going to survive coronavirus? Rather than kind of why do they survive coronavirus? That's maybe not quite the case so much anymore. There is a big emphasis currently in machine learning about kind of trying to make things like neural networks explainable. You know, so if we take an X-ray and we have some form of tumor, say, just saying that there is, yes, this person has a tumor is not necessarily helpful in order for a doctor to be able to say, to make a decision based on our kind of methods. We want to have something that says, look, this is a little bit of the X-ray that's the tumor, and this is why you should say, this is why you should make this medical decision. You know, doctors are unsurprisingly not prepared to just take a yes/no answer with no explanation before making a medical decision. And thank God, I guess. There is the kind of the classical differences between the programming languages. Different people get taught different ones, and a lot of that comes from what background these people come from. So, you know, statisticians tend to be taught R and SAS, maybe not SAS so much anymore. Data science is kind of your mix of R and Python. AI is mainly, I guess, your Python and your kind of more complex programming languages. And machine learning tends to have kind of a mix of Python and maybe MATLAB because of kind of the amount of engineers and physicists that have ended up in machine learning that haven't ended up in statistics. So that kind of brings you to the ultimate question, which kind of, I guess, every person who's applying these methods maybe wants to know, which is best. And I think, you know, the obvious answer is it depends on the situation, but I think it's important that we try to educate people on this and make them understand that just because machine learning and AI are very fancy doesn't mean they're necessarily better than statistics for everything that you want to do. I think we also need to make it more clear to people as well that statistics isn't necessarily just, you know, t-tests and means and percentages, and there is, you know, very complex statistical methods that can potentially outperform your kind of black box machine learning AI methods, because people don't think necessarily realize that in a lot of research. The other thing I kind of you have to say, I feel that this is maybe aimed at kind of clinical people a little bit, which is kind of where this talk was originally directed at, which is complicated isn't always best. You know, if we've drawn our cat on the left-hand side, that's clearly not a viable answer here, but it is an answer you could possibly get. And, you know, if on the right-hand side that you end up with exactly the same result, do you want to use linear regression or do you want to use deep learning? Well, if you get the same result, then I would definitely argue that a linear model is perfectly good and much easier to maintain and use, and has a lot less risk attached to it as well. But there is, you know, lots of applications of AI and deep learning which are useful, and if you kind of want to use these things with your work, whether it be research or industry, you have to kind of think about the situations where they are useful. So AI and deep learning, neural networks, etc., tend to be very good at image processing, which is something just statistical methods just in general can't really do. Same like natural language processing, so kind of the idea of reading text and interpreting it, so kind of, I guess, your kind of Google searches and things like that. But I've heard ridiculous examples in the industry of people trying to use deep learning on things that are very, very simple. And I would, you know, definitely argue that you should maybe not be doing that. For instance, your nice plot on the left-hand side is very much unnecessary to use deep learning on, and it will not give you a better answer. And sometimes, you know, machine learning methods don't work best. Sometimes there are just, you know, statistical ways of doing things that make much more sense and are much more rigorous for what they're trying to do. But obviously there are examples where it's much better. For instance, this swirl plot, I guess. So the thing I guess I'd say from all this is something my boss in computer science actually has said to me quite a lot recently is, you know, it's always very sensible to use statistics first. If nothing more, you have a baseline which is extremely useful for comparing your method. For instance, if we get a method that gives us incredible accuracy, but so does, you know, taking a mean and dividing it, whether it's dividing it kind of using basic summary statistics, then what's the point of using the fancy method? So you can always, at the worst, use statistics as kind of as a method to provide a baseline, or at least basic statistics, I should say, when at least you're comparing against your fancy machine learning methods. And then, you know, there are complex forms of statistics that can compete with machine learning. So a lot of people maybe still want to use AI, deep learning, because they think it's the best thing. And one thing I'd say is to talk to some experts. And I think we as kind of the stats community should do more to try and teach people that, complex isn't always better. Just because your AUC or your mean squared error is higher doesn't necessarily mean your method's the best. If you've applied your method very badly, you've not sufficiently done your kind of training and test data kind of dividing, then it doesn't really matter whether your method is better in kind of the outcomes as such. So it kind of led me to kind of come up with some conclusions as to what the difference is between the fields. And I think for me, a lot of the methods are exactly the same. So a lot of the theory is almost identical. It just turns out that some are more popular in one field than another. There is definitely a difference in attitude. Machine learning, AI, data sciences are much more modern fields than statistics, and they tend to kind of be, I guess, less held back, for better or worse, of some of the kind of the theory that statisticians have been taught that kind of stops them doing certain things. But then my boss put it to me the other day, is like, would you want a machine learner analyzing a clinical trial? Well, you wouldn't want that. Not in general anyway. I think the other important thing is there's very much a different background in machine learning statistics. Like, I've worked across kind of, the statistics department and the computer science department, and people doing very, very similar research, but the difference in the background is a lot of the statisticians have come from kind of maths, statistics, with a few kind of physicists, engineers, where if you go to machine learning, you tend to get, no mathematicians, no statisticians. You get kind of some computer scientists, some engineers, some physicists, some, very technical, very kind of technical, to me at least, subjects. And that kind of means that they have different ways of thinking and different skill sets. Basically, all in all, it means that there's a lot of practical difference between the subjects, but in theory, they're almost identical. So the final little kind of bit I wanted to talk about is how can kind of statistics stay relevant. This is almost kind of the kind of end goal of at least partial part of my talk. So the thing I think to work out why statistics, how statistics can stay relevant, is to look at kind of why people might choose to use machine learning, AI, instead of statistics. And that maybe tells us what we can do to improve and what we kind of could do, but we maybe don't want to. So I think the main one for me is programming skills. Over the last 10 years, well, since I did my master's, I think the amount of programming that's being taught in undergrad and masters is massively increased. I think we need to keep going with that, because I think a lot of the roles, at least in the kind of job descriptions that Rob kind of talked about, involve a serious amount of programming skills. Even if you're doing a data analyst role, you still need a heck of a lot of programming skills in order to do kind of a good job at it. So I kind of thought about what we should maybe teach in these kind of masters and undergrads. And for me, I think statistics needs to definitely teach Python, definitely teach Git, because GitHub and Git controller, I think are kind of vital for both open research and kind of software development and learning the skills of software development. I'd also question whether you should teach SQL, because I know there's a lot of kind of, the data engineering roles that Rob talks about. I know there's kind of a lot of your SQL, your Hadoop, and I can't remember what the other one's called. And there's a lot of these things, and I think, the more we can kind of teach people to do these things, the better kind of people are going to be prepared to do these jobs, and the easier it's going to be to hire statisticians in kind of a more wider range of jobs beyond your kind of your analytically kind of based data analysts and your data scientists that Rob was talking about. Finally, I'd almost say that C++ and Java, there's an opportunity to learn them, maybe as an extra thing. I think that's kind of a great thing to do. The other thing I think statistics should maybe do a bit more of is outreach. People talk about how cool machine learning is, and you see it in the media everywhere, but there's people doing very cool things with statistics. And I think it's pretty important that people talk about it. So kind of the media coverage of statistics isn't just, clinical trials and, results of whether P is less than 0.05, which a lot of kind of the media coverage tends to be. The other thing I think is kind of really important, I think, again, statistics can kind of, in general, improve on a lot, is kind of implementing your work. There's kind of an attitude difference between machine learners and statistics, in the sense that machine learners tend to fit a reasonably simple or a kind of a black boxy kind of method. They implement it in practice and they make sure that it's available for the people that want to use it to use. Whereas statisticians tend to fit, potentially a better model, present the results, and then, well, they don't really do anything about it. It's not working again. Yeah, they don't do anything about it. So I think that's something we can improve on. So, prime example is me, who, despite the name on the Zoom call, Vinny. After my PhD, I did not put my code on GitHub. I should have put it on during my PhD. I didn't. I didn't put it on after. It took me 2 years to put it on GitHub. So, the people that wanted to use my code, if they wanted to use my code, couldn't, even if they wanted to, which is silly. Whereas kind of in computer science, there's this big focus on making sure that the code is available for people, making sure that if we design our code in a way such that someone can go ahead and use it, that is designed so that people can use it and it can be used for multiple things and reused. I think that's something statistics can maybe improve on a bit and kind of make it a little bit more useful for kind of upskilling people and making them relevant for the various job roles. So for that, I think, GitHub is a very easy solution. I know people like R packages, but for me, GitHub is a much easier, simple version to do, and it's really easy for people to download and use the code. And I think it also just encourages people to write cleaner code. The other thing is to make sure to help others implement it. So a lot of statistics people I've seen don't tend to kind of get involved when helping the user actually use the thing they've designed. And I think if people were to put more time into that, I think that would be something that would improve the kind of the reach of kind of statistics in general. So in order to do that, we have to allow time in projects for people to actually do this. And, my final thing is I think we should teach kind of students Git control, and especially kind of dissertation students. Why can't they just put it on GitHub and they just learn something new as part of the process? So kind of the final things I kind of having kind of read goal of kind of this session was to kind of talk about why people should maybe employ statisticians, why Rob should be picking a master's student from statistics, as well as a master's students in machine learning or data science. So I think for me, statisticians maybe have a slightly better understanding of data than maybe some of the kind of data science machine learning people, at least people from a statistics background, that is. They're probably better at describing data and giving more relevant summaries. And they're also probably more likely to think about some of the implications of kind of what they do with the data. I've used the classic kind of World War II, is it a bomber or a fighter plane? I think it's a bomber, right? And I think a statistician is much more likely to realize why the kind of analysis that said, these are the spots we need to add extra armor on is incorrect. And I think that's maybe more likely than someone from a kind of more programming computer background. Finally, I wanted to have my say on writing job adverts. I think Rob's actually kind of covered most of this, but I guess this is my experiences more as a candidate rather than someone writing it. For me, I think companies need to, stop writing unrealistically long wish lists and maybe think about what they actually want rather than just kind of writing everything they think is relevant. I think they need to maybe be more sensible with their candidate expectations. A lot of the job applications I've seen are wanting an insane list of skills, but not offering kind of the money to kind of represent that skill level. And I think when you do that, you end up with a candidate that can do a tiny bit of everything and is maybe, not capable of doing the job that the company actually wants. The other one I would say is don't put the most techie words you can think of, which I guess is maybe the kind of the bit that comes from the C-suite, I think Rob called them, the kind of the upper levels of these companies. If I see reinforcement learning and t-tests in the same sentence, I kind of automatically conclude that the company has absolutely no idea what they're on about. And I think the other thing that I think companies could be much more clear about is the amount of software development that's involved in a role. As kind of Rob said, that you should definitely ask that in a job interview, but I guess I'd like to see that more in job adverts themselves as well. You know, I've seen various situations where statisticians effectively are getting hired as Python programmers, and just, you know, that role's not suitable for them. They can do it, but they're just not going to be doing it at the level that maybe the company is expecting them to do it. So the actual final bit now. Am I a statistician or a machine learner? So I've worked in statistics, worked in machine learning. People have asked me this. Job interviews, people have asked me this. This is kind of how I feel like in a computer science department. This was meant to move, but if you've seen the IT crowd, you'll know that Jen thinks that has been told by the IT guys that the internet is a small black box with a light on it. That's kind of how I feel in the computer science departments. It's hard to call myself a machine learner. So I think I'd say I'm still a statistician at heart, but I'm trying to improve my kind of coding and software development skill levels to try and make the things I do a bit more kind of useful and applicable to the people kind of I'm doing things for. But I would always say that I would always use statistics first and then machine learning second. Yeah, and that's the end for me. Thank you.
Thank you, Vinny, for your great contribution and great presentation. I certainly have a whole bunch of questions, but I think that there are more questions that have come up in the chat. There's a larger overarching question that I want to get to in a second, but I would like to do some sort of rapid fire questions, and you can sort of try to reply with what comes off the top of your head. The first question would be, why is the word deep appended to labels? And do you think that this is a useful differentiation? Deep learning, deep, well, I don't know what other deeps are there, but it's more, does it really go that deep, or is it really that deep?
It's an interesting question. Again, my boss actually asked me this the other day. It's like, what do you consider to be deep learning? Because at the end of the day, deep learning is just a neural network. It's just how many layers you put into it. No, personally, I don't think the word deep learning, adding deep to things is necessary. You may as well just call it what it actually is. But I guess that's my skeptical statistical opinion. So you'd maybe want to ask someone that's more computer sciencey based what they think.
Rob?
Because how do you define deep? Like, is one?
I'm the last person in the world to define computer science or data science, but my observation on this would be, if we were all to jump in our time machine and go back 20 years before we started seeing data science appearing everywhere, we're now seeing deep appearing everywhere. I suspect the C-suite have got a hand in this. It's a cool buzzword. Let's call everything deep.
Very good. Next question. Do you think that machine learning technologies will take over roles such as data analyst and coding to be done automatically?
I think one of the things that I'm seeing, particularly within larger organizations, is what's called self-serve analytics, where the data team will build a number of push button type reports, dashboards, graphical representations that effectively mean that the data analysts don't need to do so much of the mundane stuff. Yes, I could see a time when the machine, be it a machine learning algorithm or whatever you want to call it, actually does mundane data analysis. Yes, I could see that happening. Don't know if it'll be in my lifetime, but yeah, I could see that.
Yeah, I think you're right. You can definitely replace certain roles right now, certain bits right now with kind of automated stuff. But I don't think we're very close to the stage that people need to be worrying about their jobs because of machine learning.
Yeah. Great, thank you. And the bigger question that I've seen in the comments and in the chat is that there's this issue with framing, and Vinny, you had a couple of slides in your presentation about it, and I guess, Rob, you tried to do a really good effort in separating the things that need to be separated. But should statisticians frame themselves as programmers? Is it necessary to get a job in data science, or is a statistician an individual dressed up as a programmer, or vice versa? And how to sort of talk about how I should sell myself and how I should ask for people to join my company.
I don't think. Oh God,
Vinny, you want to go? You go first.
Okay, I don't think statisticians should frame themselves as programmers. I think that's kind of a nightmare waiting to happen, because you wouldn't want to get a job as a programmer if that's not kind of what you are. But I think statisticians should be trying to demonstrate that they do have the programming skills that are needed to interact with someone that's a programmer, right? Because if you go work for a company or you go work at the university, you need to be able to kind of work with someone that is doing the kind of the technical kind of programming side of things. And if you can't do enough programming to kind of get to a meeting point where you can talk to them, then you're going to have issues.
Yeah, I think statistician can be one of two things. A statistician can either be a standalone expert in their own right, an expert in statistics, or that statistical knowledge can be one of a toolkit used for certain other roles. So for example, data analysis or data science or data engineering. So I think, to echo Vinny's point, it's very important that firstly, the individual determines what they would like to be. And I spoke about the kind of tools expert at the various levels of the hierarchy. There's a hierarchy just for statisticians that could be tools expert in statistics all the way to the end of their career. But firstly is honesty with oneself. And then secondly is an understanding that, well, if you really want to be a programmer, you will still be welcomed by a lot of organizations who recognize the discipline of a foundation in statistics as being something that would be of benefit to a programmer. But it would be down to the individual to say, I trained as a statistician, I want to be a programmer, or I trained as a statistician, I want to stay in statistics, or I want to move into data science. So it's either thoroughbred or very useful component of another career direction.
Great. Yeah, I think that's a good summary. I have a question that I had that came up during your presentation, Rob, was it seems like to start, or for a starting position in a data science job, you need to be able to do everything to then specialize into one of the two branches that you mentioned of being a data manager or being a data analyst. But what I see from job ads is you need to be able to do everything. You need to be able to do DevOps. You need to be able to do the statistical intent behind it. You need to do the programming. You need to do it. It seems very daunting to apply to one of these jobs because, as you said, companies don't really know what they're asking for, and so no one can be all of those things at the same time.
Yeah, it's something. I mean, there's probably a post a day on LinkedIn talking about this very specific point. The reason that I put together the slide that I put together, which talked about the technical people coming up with their wish list and going to the human resource team and being augmented with a whole load of other stuff, then it going to the heads of or the C-suite. This is what is happening, but it's what is happening is as a consequence of, I don't want to say data science is a new field. I know it's not a new field. Commercially, it's new in that it's only been recognized for around the last 10 years. The hype train is still in motion. Organizations, generally speaking, do not know exactly what they need. It's the reason why guys like me are in existence, because we can say to an organization, I've read your job spec. 3/4 of that is superfluous. You don't need it. What exactly do you need this person to do? I need them to do this, this, this. Right, okay. Your job description's now that size. We can find you the right person. Another point that I would add to it, Sebastian, which is it also very much depends upon the size, complexity, and maturity of the organization. So, for example, in a startup, yeah, the likelihood is if you're the only data scientist, you will have to do everything. So you're going to have to be really, really good. Whereas if you're joining a data science function within an established business, they will already have sub-specialists for different areas. You know, they've probably got the machine learning guys there, the visualization guys there, the analysts here, the statisticians there. So in a larger organization, you would be much more likely to enter as a junior or graduate level position in one specific subsector. But in a startup organization, you may well have to be the all singing, all dancing data science guy. You're going to have to do everything.
Great. Yeah, Vinny, do you have anything to add to you on that? Or
No, that's definitely Rob's area. Let's leave that to him.
okay, Rob, I have one last question for you, which is someone wanted to know what the ratio of quality applications to total applications you get for entry-level positions.
Sorry, could you ask the question again, Sebastian?
If you could share the ratio of quality applications to total number of applications for an entry-level position.
Well, it's a hard one. So the organization I work for are a very well-established, well-known specialist organization. If we put an advert out on the internet, it tends to be a very well-written advert, going through that process that I mentioned, where we've done a deep dive and said, look, yeah, I get what your HR department have written, but what do you really need? Our ratio of applications it's usually fairly strong. We usually only appeal to people who have actually got the skills to do the job. But our primary method of finding individuals is not necessarily in response to an advert. Adverts have a dual purpose. The first purpose of an advert is to act as a very large net that's cast into the ocean. You can't guarantee who's going to respond to that advert, hence the point about ratios. But the way that we most normally find individuals is by very targeted approaches. And I do a lot of work around social media use and how to maximize your social media profile. Because if your CV sits in a top drawer and only sees the light of day when you're applying for a job, your LinkedIn profile is a 24/7 version of your CV. That's what should reflect your up-to-date skills, because that's the most likely way of individuals like me interacting with you. So I would say when we advertise, we tend to get a very, very good response. But that's not the primary way that we find talent for organizations. The primary way that we find talent for organizations is by directly approaching individuals who have either got a very distinct LinkedIn profile that's got the keywords we're looking for, or we know them through previous relationships like this type, some of the community stuff we're on, or the academic collaborations that we've run in the past. So we've got we don't rely on throwing a net into the ocean, if that makes sense.
Yeah. You're more specialized in that way. So
very, very specialized.
Okay, great. And Vinny, I have one last question for you. Someone wanted to hear your opinion on calling algorithm auditing as an innovation in the data science world. And this is when you were speaking about the black box analogy.
What, sir, was that?
So they want to hear your opinion on algorithm auditing.
Algorithm auditing?
Yeah, as an innovation in itself. The question, that's exactly what the question reads. I don't really know what.
I don't really know. I'm not sure
Adrian,
I know
Adrian, if you are still in the call, maybe you would like to expand a little bit more on what you meant. Maybe you just unmute yourself and ask Vinny. Adrian does not seem to be.
Can't unmute.
One second.
Oh, you'll have to unmute him, I think.
I have to unmute him.
Oh, you can ask to unmute, by the looks of it.
Oh, have no mic. Oh, well,
If you just tell me what you mean by algorithm auditing, then I can maybe give you more of an idea. I'm not quite sure what you mean by that, sorry.
we're all cheering for you.
Auditing in the future akin to financial auditing. Oh, you mean whether kind of how you can audit whether you can audit machine learning because it's kind of so black box. Okay, I see what you mean. Yeah, I mean, I think with all machine learning, I think with kind of machine learning that's all about prediction, I think you have to kind of accept that that there is a weakness that you can't necessarily see how you get from your original data to your kind of predictions. And I think if you use it, you just kind of have to deal with that. That's kind of in a sense why in things like clinical trials, you don't really see machine learning because you just can't explain how you got to your answer. There is a lot of work at the minute with kind of neural networks, deep learning, that kind of thing, about trying to make the neural networks themselves explainable and kind of see what is causing a prediction to be one thing or another, which is kind of interesting. But I think it very much will depend on how much auditing you need to do for whatever it is you're doing as to whether you can get away with one of these black boxes or not.
Great. Well, thank you both very much. We appreciate your patience in, well, everyone's patience in making sure and listening to Vinny and waiting for Vinny to solve his internet situation. And Vinny and Rob, special thanks to you. We wish to have some mince pies for you, but maybe next year you can join us for the next AGM, and then we'll give you a double portion.
That would be an absolute pleasure. Thank you so much for inviting me. Thanks for hosting. Thanks for everybody's interaction. Thanks to Vinny. Thank you. It's been an absolute honor.
Yeah,
Thank you.
Thank you for the invite.
And thanks everyone, and I'll see you next year, hopefully. Bye.
Bye-bye.